again, wasn't planning to make any presentations today, but I want to quickly get to one point which I think we'll make today and again in the fully convolutional neural network for semantic segmentation. There's another paper down the line that's coming which will use this idea of deconvolution. How many people have heard deconvolution or inverse convolution or backwards convolution? Some ideas like that. Okay. I think it would be good to sort of just clarify a couple of things. Quick thing, homework 2 is, you're still working, some of you are still working on homework 1. Homework 2 is out tonight. I won't go over it right now because there are 2 presenters behind me. I don't want to run over their time, but we'll look at that on Thursday. It's due in 2 weeks. The project proposals are due in a week or so. This is, again, something that I don't want to go into a lot of details right now. We can go over on Thursday, there's only one presenter then. But it's just a simple, we'll hand you a sort of web page template. You just have to write a couple of things like an abstract, a picture, and some goals. Like, what will you work on? What's the idea? This is the standard thing is that if you've taken my intro to machine learning class, you've sort of already done this, except this is not in any conference format. This is in just a web page format, so that at the end of the semester, you'll update this with your results. But in any case, so this is, keep this in mind. We'll get into more details on this at on Thursday because we have more time on Thursday. But I want to get to this one topic and then hand it over to the presenters. All right, so let's talk about deconvolution. Let's start with, I'm going to start with a simple one-dimensional example because it will make the connection much clearer, and then we'll generalize it to a two-dimensional example. So you remember Toeplitz matrices, right? The idea was that this is a matrix which has constant diagonals, and we care because we can write discrete convolutions as matrix multiplications with the Toeplitz matrix. Right? We showed you this particular example. You sort of take your input, y is equal to hx. You take your input, you string that up as a column. Each row of this is trying to do one particular dot product, right, with a shifted version. And throughout the lecture, whenever I say convolution, I really mean cross convolution. So that's a little confusing, but imagine that there's no flipping of the filter happening, right? That all that has already happened. You have that filter, we're sort of sliding it across. That's what each row is doing. Sort of h1, then it shifts a little, then it shifts a little more. That's what each row takes a dot product. That gives us the output. Okay. Deconvolution, or more specifically, non-blind deconvolution, is asking for the inverse of the process. I've given you a y. I've told you the filter. Find me the x. Okay? That's the operation that you're being asked. If you just think about this for a little, this should be possible, right? Each row here, right, there's n unknowns and there's n equations. Each row is giving us a linear constraint. Right? We know h1 times x1 is y1. Right? We know h1 times x2 plus h2 times x1 is y2. So there's a bunch of constraints, there's a bunch of unknowns. This should be solvable. Okay, so this is a linear system, solvable. But what we'll do is we'll make a particular assumption here that will make our life even easier, right, than the general case. Does that make sense? All right, so let's make that assumption. Y, it has y1 to ends. There's some matrix of filters H, and this is my x. This is x1, xn, and sort of draw filters in a special way that the filter sort of has one entry here, that's two entries here, 3 entries here, and it's sort of sliding across all the way to that one has 1 entry here. Okay. I'm going to make a assumption that the columns of H are orthogonal. Right? It's not always going to be true, but if that were true, it would simplify our life a lot. So for example, here's an example, right? Here's a one-dimensional filter, +1, 0, -1. What does it do? Edge detector, yes? It's a one-dimensional edge detector. You sort of splay it out on the rows here. What happens? Here's what this looks like, right? You sort of get these things where this one will be, which one are we going first? Let's see, +1 here. Then there's +1, 0, +1, 0, -1, +1, 0, -1, and so on, right? So that's sort of what this matrix looks like. Now let's consider a particular, this column of this matrix and this column of this matrix. Are those columns orthogonal? Orthogonality here means dot product is 0. Is that true? Yes. So for some filters, if you design it right, you take the dot product of the columns, they're going to give you 0. Are the norms of the columns 1? L2 norm is not 1. You just have to scale it a bit. Right? If you divide by square root of 2, then the L2 norm becomes 1. Okay. Why do we care? Why does the assumption help? If the columns are unit norm and the adjacent columns or all pairs of columns are orthogonal, why does that help? So for the norm of the filter, forget about it. That's controlling the intensity, right? Forget about that for a second. But if I have a matrix whose 2 columns, anytime they're not identical, the dot product is 0.
Basis vectors.
Basis vectors, very nice. So this is an orthonormal matrix or an orthogonal without the unit norm assumption. And they end up forming an n-dimensional basis vector. So you're sort of taking from one coordinate space, moving to another coordinate space, right? You're just projecting it along these basis vectors. Why does that help? If you solve a linear system, and so, for example, now we need x, right? We're trying to solve, we were given y is equal to, let's say this was hx. If h was orthonormal, then x is equal to H transpose, that's right. You get x is equal to H transpose y because you left multiply by H transpose on both sides. This is H transpose H, you get identity back, that sort of goes away. Okay. Things from linear algebra, studied them a long time ago. Okay, so that's why if you make this assumption that your filters are orthogonal, shifted versions of filters are orthogonal, it sort of saves your life a lot. You can do deconvolution with such filters really easily. This is very easy. The other thing that it sort of provides an intuition is, what does this look like? What does x is equal to H transpose y? There was a signal, there was some convolution, we know what the convolution was, we recorded the output. Now we'd like to know what the original signal was. The way to do it, the math tells us, is take this matrix, transpose it, multiply it by a vector. But what does this look like? It looks like this, right? So H transpose. This thing had shifted versions on the rows, so H transpose is going to have shifted versions on the columns, right? There's 1 entry here, there's 2 entries. I'm going to assume a length of 3 just to make sort of my illustration easier. There's sort of 3 entries here, then it starts shifting and so on. Does that make sense? And this is just sort of x is equal to H transpose y. So H transpose has the filters on the columns, right? H had the filter shifted on the rows, this is the filter shifted on the columns. So that tells us that if you want to reconstruct the signal, you should take sort of these shifted versions of the filter and add them up by weighted combinations of the output, right? So if I just write this thing out, this is a matrix vector product. It means there's y1 here, y2 here, all the way till yn here. This summation is reconstructing this original vector. Does that make sense? Okay. So far, everybody with me? Okay. So all that you have to do is you have to take your input filter, sort of move it around in various places. So place it at one place, place it in another place, place it in another place, place it in another place, and sort of add them together by sort of overlapping. How would we do this in a 2-dimensional case? It's quite simple. The operation for a 2-dimensional case is quite similar. You sort of have an image. This one is n by n. This is our x. You have a filter, which is k by k. this convolution produces, let's say, a y, which is, let's say, it continues to be n by n. This is the forward convolution process. You're now given a y, and you're asked to deconvolve it. Right? If you stare at this, all that it's asking you to do is, the way you do it is, I'm going to draw the filter with this color yellow. So you take your filter, place it at a particular location, multiply that by y0, comma 0, right? That's this entry. Right? So you place your filter at this location, multiply by a scalar, move that filter around just a little bit, off by 1 pixel, multiply that by y1, 0, comma 1, and you sort of are adding these things together, right? This superposition is giving you back the input. Does that make sense? This is the 2D version of this 1D thing. Right? You have these 1D signals shifted around, added together by linear combinations given by y. This is 2D filter shifted around, added together, superimposed together by linear combinations given by the index y. So far, so good? Okay. The reason why all of this is interesting is that this operation of deconvolution, if you contrast it with convolution, the way we convolve is we do something similar, right? We place this filter at this particular location, we take a dot product, that gives us this entry. So convolution has this notion of sliding and dot product. Deconvolution has this notion of sliding but superimposing, right? You sort of add them to weighted combinations. Does that make sense? Okay. Convolution has this notion of input stride, right? You could skip on the input level. Deconvolution has a notion of output stride. You can skip, you don't have to move the filter just by 1, you could skip by 2, and so now input strides in convolution shrink the output down. Output strides in deconvolution scale the output back up. Does that make sense? So this could be n by n. If you're using a stride of 2, this would be n over 2 by n over 2. If you're using an output stride, you can start with n over 2 and get back n over 2. Does that make sense? This is going to be useful a lot in some of the later papers where they're going to have a convolutional neural network which over the layers is sort of shrinking down the feature maps spatially, but at the end you want a full sort of segmentation of the image, and you want that to be the full size of the input image. So at some point you have to do a super resolution operation, which is what you will sort of do with these deconvolution filters.
I didn't understand.
So convolution has input strides, which means you don't have to put the filter down at 1 pixel adjacent locations, right? You could put one filter down here, and then this is non-overlapping convolution, right? You put the next filter down, and what does that do? It basically takes your input and it scales it down by the stride length. Right? So if your stride length is 2, it's sort of scaling down your input, so this will become n over 2 to n over 2. Similarly, deconvolution has an idea of an output stride length. So you don't have to put your filter down at adjacent locations, you could put them slightly farther apart. Right? So you could put this filter down here, and you could put this filter down here. This thing is an upscaling, is an upsampling procedure on this, right? It takes that pixel value and it blows it up into a k by k region with a constant. Right? So this is y0, comma 0. It's placed here with this particular filter. Let's assume this filter was constant for now. I'm just giving an example. So this would be a nearest neighbor up interpolation upsample. Does that make sense? So this is an idea of an output stride. Just like a greater than 1 input stride scales down an input, a greater than 1 output stride scales up an input. Okay, so that's good. So you can have this sort of an intuition in your mind anytime people say deconvolution, but that's not how these things are actually implemented. The way these things are actually implemented is using convolutional primitives. So you can, it's good to sort of view this as, oh, actually before I go there, this was two-dimensional input, two-dimensional filter, two-dimensional output. In a regular convolutional neural network, this thing is a 3D volume, right? There's sort of C1 channels here. And this thing is a 3D volume as well. There's sort of C1 here. You sort of place this 3D volume here, take a dot product over all dimensions, that's what gives you a pixel. We can do that same thing in the deconvolution stage. There is one feature map here, there's a 3D volume. In order to reconstruct the input, you put this 3D volume down at a particular location, you multiply by y0, 0, move that filter apart and start adding superimposing 3D volumes. So first do it? Okay. So that part's clear. So you can view these things as either as sort of superimposing a bunch of volumes, but there's another way of viewing it, and that requires us to go back to the 1D intuition. And the 1D intuition says, look at any particular row of this process, right? So there are columns which are shifted filters. This y is a column vector. It's multiplied here. Let's look at any particular row, which means how exactly is the input dimension xi being reconstructed, right? That's what we're asking. How is this being reconstructed? And for sake of simplicity, let's assume we have this filter, right? It makes, we don't really have to use these numbers, but we just have to use that this is h of 0, this is h of -1, this is h of +1, right? Notice I've done origin centered at 0 and things going into negative indices. Just bear with me for a second, right? Just, this is a filter which is centered, it has length -1 to +1. Okay. That's what these things are, right? Let's try to reconstruct this. This xi, it takes this h of 0 times, there's a yi here, right? That's what gets added up to get this pixel. So this one pixel here is contributing to this entry here, right? Then there's this one pixel here that's contributing the shifted version before and the shifted version after, right? So there's this filter, this one entry is going to. Does that make sense? Okay. And I'm going to write them down. They're going to feel like magic. If you just do it on your own, you'll see the same thing. It's basically this idea that you get h of, so this thing is h of 0 times y of I, right? That's this number copied here. H of 0 times y of I. This thing is h of +1 times y of I minus 1, right? That's this number, y of I minus 1, h of +1, and the third thing is h of -1, y of I plus 1. So the thing just over y of I plus 1, h of -1. Okay. Anybody want to tell me what this expression is?
Convolution.
It's a convolution, except if they were slightly different, for example, if this was, so this part is correct, if this was h of -1, y of I minus 1, h of +1, y of I plus 1, this would be a cross correlation, right? It would just mean take h, put it on y, that dot product is giving you x of I. Because of these +1s, -1 shifts, it's because you put the filter down a rows and there's a transpose that happened. This means that you take your filter and you have to just invert it and then do cross correlation. That's what this operation is. Right? So you are correct that this is convolution, but I'm just trying to explain that this is flipping and then cross correlation. Right? Which tautologically is true, but let's just be precise, because at the start of the lecture I said every time I say convolution I really mean cross correlation. Here it sort of betrays that. Does that make sense? Okay. So we can view this procedure as placing down a bunch of filters and superimposing them. Or we can view this as taking your output y, taking your filter, flipping it in x and y. So the first dimension flips and the second dimension flips, and then just do a convolution. That's going to give you your input. Does that make sense? So the intuition comes from one dimension. Filters were on rows. The inverse required transpose. We could view it as summation of columns, or we could start viewing it as for each row separately. And that's what giving us the flip the filter and perform a convolution. Everybody with me? Okay. That's how these things are actually implemented. Yes?
How is the depth being reconstructed?
So the depth is not being sort of in this splicing view, the depth is what it is, right? Every time you splice down this thing, you're sort of you're placing down a 3D volume. Does that make sense? So
that
in
filter
this,
is a volume and the feature map is a 2D map.
this feature map is a 2D map.
Right.
That's right.
So, I mean, I can't understand like.
So so let's go each view at a time. So the first view is superimposition view. In superimposition view, you take your filter, you sort of place it at a location. Your filter is a 3D volume, so after you place it, you get a 3D volume back. You move it around in only 2D, not in 3D. And that's why you get a bunch of superimpositions, but the output is still a volume. Right? In the convolution sense, you treat each one of these as a map, convolve it with this, and that's what is giving you this sort of three-dimensional point.
So I can imagine that slicing it down into some n number of filters.
See one number of filters. Yeah. Okay. Yes.
So in this matrix right here, the vertical lines, each of those red lines represents this filter, right? Plus 1, 0,
That's
plus
right.
1. So it looks like yi is multiplied with h of 0.
Yeah.
And then yi minus 1
Yeah.
seems to be multiplying with
H of 1.
plus 1.
Yeah. Exactly. It's because they were like, this was cross correlation, right? So the filter was moving this way, and so the filter is moving down this way. Makes sense? Okay. So this was like a really short tour on deconvolution. Most of you should sort of view it as convolution as sort of a forward pass, deconvolution as a backward pass. It's like a very special backward pass where it takes an activation and performs a 2D convolution again with flipped filters to give you back something of the same size as the input. And you're going to see this in two contexts. Number one context is when you need to sort of upsample to get a semantic segmentation map. And that's going to happen in another paper down the line in the class. Today you're going to see it in the sense of visualizing. So we're going to feed in an image, it's going to give us an activation map. We're going to set all other activation maps, for instance, to 0, try to understand what does this activation map do, and then we'll try to reconstruct back to the previous layer. What is the previous layer activation that caused this? Right? And then we're going to propagate all the way back to the image space to see what does that look like. Does that make sense?
This is exactly the same as backprop, right?
This is exactly the same as backprop, with a couple of operations flipped, right? If you look at, actually one of them is covering the Karen Semyonov paper, and they'll make a connection to it. So I'll just wait for that slide. Him and then you. Yeah.
So autoencoders, this is similar to that. You have an encoding operation one way, a decoding operation the other way.
It will come down to the objective. Autoencoders are trying to reconstruct the input. Here the objective is not that, right? In different contexts, so we're going to ask, what is this filter that we're using? It's the original filter, right? It was trained to do something, right? So that was the objective for which this filter was chosen. Autoencoders have a sort of layer where the filters are trying to reconstruct the input and the loss penalizes them for that. And in the fully convolutional paper, you're going to see where deconvolution layers are used to upsample, they do actually learn a completely different set of weights, which are deconvolution weights, for semantic segmentation accuracy or whatever.
And as far as the first layer is concerned, it's mostly when you're trying to even do the same operation, the first layer is so general that it's more of a reconstruction problem, isn't it?
But that's not the objective.
Okay, right, I understand that. Okay.
Yes?
You mentioned you were able to reconstruct X because all of the columns were orthogonal.
Right.
So is that going to be true for all filters you apply, or are we just kind of assuming that it's going to be orthogonal?
Nope. If you assume that good things happen, in practice, that's not.
It's just like a best guess.
It's like a best guess.
Okay.
So when you're going to view this as an upscaling layer, it won't matter.
Okay.
Right? Whatever it, like this is just a procedure, and we tune the parameters of this procedure to do well.
Yeah.
In the visualization case, it's an assumption, right? It's sort of just a heuristic that if these assumptions were satisfied, this would be a good thing to do, and let's look at what happens even if these assumptions aren't satisfied.
You shouldn't even expect to be able to reconstruct it. If you
downscaled
it to be
if the matrix isn't like if you're taking longer strides, then you sort of have this linear subspace. You won't be able to reconstruct it. Like there's just sort of a null space where you can't tell.
And if you're learning parameters, then this whole notion goes out of the window.
Yeah, if you're treating deconvolution as an upscaling layer, it doesn't really matter. It's just a procedure that gives you an upsample mask, and you're learning parameters of that procedure. Okay.
Yeah,
I mean, one fine of
say,
it.
since we already have the original image, it is the reconstruction, perfect reconstruction of the concept.
But we want to see what the, like in visualization cases, we want to see what the network is capturing, right? So if we're trying to visualize, then we can't look at the original image, which is actually something that we'll see in some of the figures today, right? That the reconstruction tells you that it's not the full patch that was causing large activations. There are certain regions in the patches that was leading to large activations. Okay, where's our visual? Let's get started. Where's our presenter? Yes, let's get started.